All right. I think it's fine. So good morning to you all. And today this is going to be part 19 of our control system engineering and part 2 of our discussion on root locus. All right. So again, as usual, we are going to start from where we left off in our last discussion. And we were actually constructing the root locus for a certain transfer function. And along the way, we were trying to figure out the underlying rules behind the construction of root locus, right? So yes, our objective here is to figure out how the closed loop poles of a system travels really, okay, when we change the gain. As we keep on increasing the gain here in the forward path, how the closed loop poles behave. That is the figuring out how the closed loop poles behave is the whole purpose of this thing, right? As usual, we know Routh-Hurwitz theorem, Routh-Hurwitz criteria here, and that kind of gives us an idea on the ranges of k for which the system is stable and range of k for which the system is unstable, marginally stable, etc. But here, using root locus, we also are able to figure out how kind of the damping ratio of the system, the undamped natural frequencies of the system. So we kind of figure out how the system really behaves, apart from just knowing whether the system is stable or not, right? So that's kind of the purpose here. And also the entire thing builds upon the fact that we didn't have calculators back then, so we don't really calculate the poles, we don't really solve the characteristic equation, but actually without solving the characteristic equation we try to figure out the locations of the poles, closed loop poles, depending on varying values of gain k, right? So yes, so as we increase the values of increase the gain k, we see that the roots, or essentially the closed loop poles, do travel along certain paths, and those paths are called the for a single point there, we call that a path traced by a single point is called the locus. And since we have multiple poles, we have we call it root loci ideally. Okay, so it should really be root loci. So let's change the name. Okay, let's make it proper English. Okay, we should really call it root loci, right? So plural of locus. All right, so with that said, so if you recall, we kind of figured out three very important things about the root locus, right? First of all, root loci are symmetrical about the real axis. That has to be true, right? Because the polynomials we are essentially trying to solve, or maybe not solve, they have real coefficients. And this is one of the fundamental theorems in algebra, that if you have a polynomial that has real coefficients, the roots of that polynomial can only be real or complex conjugate pairs. So in that sense, we know that the root locus has to be either on the real axis or complex conjugate, or have points complex conjugate point pairs, right? So that way the root locus has to be symmetric about the real axis, right? Then we also figured out which parts of the real axis can be on the root locus or cannot be on the root locus based on the satisfaction of the angle criteria, right? And when parts of the real axis are on the root locus, we also figured out what the gains or the subsequent gain values are, right? For what gain parts of the real line are on the root locus and not, maybe, right? So we figured those things out, right? And we also talked about breakaway and break-in points. So we figured out that if two roots travel towards each other, two or more roots travel towards each other, there might be a situation that they meet at a certain point. So I would have coinciding roots for a certain value of gain k, and then after that the roots will again diverge from each other and go in their separate directions. Okay, those kind of things, those kind of points at which these kind of things happen is called a breakaway point. So the roots meet and then break away. The other thing might also happen in a similar fashion, that two roots coming from two different directions that previously broke away, then they would meet at a certain point, most likely on the real axis, but they could also meet on the entire S plane, anywhere in the S plane as well. And after meeting, they would travel in other directions like that. So those points are called break-in points, right? They have a subtle difference, and we are going to see examples where we have both breakaway and break-in points. But again, this is built upon the criteria that how do we figure out that a polynomial has more than one roots at a certain point? By simply differentiating the polynomial n number of times, and if we get the same root n number of times, even after differentiating the polynomial n number of times, we say that root is there in the polynomial n plus 1 number of times. So that's the idea here, right? So that way we essentially differentiate the characteristic polynomial essentially with respect to s, and once we do that, we solve for it and make it equal to 0, and we just essentially solve for it, and the points we get essentially are the points at which those kind of double roots or triple roots or four roots kind of quadruple roots could happen, right? So essentially those are the breakaway and break-in points. Oh, someone is asking a question about route table, right? So I think I need to take, of course I need to take another additional classes through Google Meet, and just to make sure that you understand the difficulties in route table. Someone is asking about the difficulties in route table. Okay, difficulty 1 actually ensures that the system is unstable, right? And I can prove it if you are willing to spare that amount of time. Okay, difficulty 1 would always ensure that the system is unstable. Difficulty 2 might result into a system that might give you you might get difficulty 2 for a system which is not entirely unstable, okay, also not stable. So you might get difficulty 2 for a system which is marginally stable, right? But you can also get difficulty 2 for a system which is unstable, right? But if you get difficulty 1, then the system is definitely unstable. So there is a way in which you can prove this. But there are few nuances in that definition here. Difficulty 1 can arise at any row. Okay, it can arise at s to the power 1 row, s to the power 2 row, s to the power 3 row, and such. But if you solve a few problems, you will see that difficulty 2 would only arise at odd power row. Essentially what I mean, difficulty 2 can arise at s to the power 3, s cube row, or s to the power 1 row, or s to the power 5 row. So difficulty 2 can only arise at s to the power odd powered rows in the route table. So that's a discussion, and that can also be very easily proved, really. Okay, so again, that's a very simple thing, but we can indulge ourselves in doing those discussions at a later point. But you have to understand that when you encounter, and for that matter, if you encounter a 0 in s to the power 1 row, right? If you encounter a 0 in s to the power 1 row, you can assume that to be a difficulty 1, also as a difficulty 2, because s to the power 1 row only has one element, and if that particular one element is 0, you can imagine that to be a case where the entire row is 0, right? S to the power 1 row has only one element, and since that one element, if that one particular element is 0, you can assume that the entire row is 0. So you can treat it as a difficulty 2, or you can treat it as a difficulty 1, right? But again, the idea is that whenever you have a chance of considering something to be difficulty 2, choose that. Again, there are reasons behind those things which can be proved very easily mathematically. Okay, someone is asking how can we check whether a system is stable or unstable if it's a difficulty 2, right? If it's a difficulty 2, proceed the way you do, right? So if you encounter a difficulty 2, just create the auxiliary equation, construct the new modified row, replace the row where you encountered the difficulty 2, and proceed. And subsequently, if you have sign changes in the modified route table, okay, if you have sign changes, then definitely you have poles on the right half plane. In that case, the system would be unstable. But if you encounter difficulty 2, but yet you don't encounter any sign changes in the first column of the route table, that indicates that there are poles on the geometry axis, but the rest of the poles are on the left half plane. So the system would be marginally stable. Right? I think I answered your questions. If you still have more questions on this, we shall resolve those in a Google Meet class, right? All right. So that is something we discussed here, right? So I think this is quite easy to understand, right? So there is one thing I kind of skipped, didn't really discuss properly. If you recall, now let's start our discussion, start our today's discussion, right? So we saw that when we started with gain k equal to 0, these were the locations of the closed loop poles. Essentially, the closed loop poles were at the locations of the open loop poles, right? So at s equal to -2, s equal to -1, and s equal to -3. Now these two roots behave this way, that the roots at s equal to -2 and -1, they approached each other, right, in this direction, and they met at a point s equal to -1.42 when the gain k was 0.385. You understand this, right? And from that they departed, right? From that they departed, right? Something like that. And so this was the breakaway point, right? Now notice very carefully, I did make them depart. What was the angle here? What was the angle of breakaway here? The angle of breakaway was 90 degrees, right? Plus minus 90 degrees. So this is kind of a true fact. So for example, this is something we are going to start our discussion today with, right? So this is the thing that we kind of missed in our discussion. So notice very carefully, something like this could happen, right? Say we have two roots, right? Just imagine something like this. We have something else, of course, here. Just imagine there are two roots and these are approaching each other from different directions here. And if there are two roots and they approach each other, and then at a point of breakaway, they break away from each other, they would share the angle equally. So essentially, they break away in a manner that does not violate the rule number 1. So all the rules here are complementary to each other, right? One of the rule, you cannot have one rule that violates the other, right? So if two roots approach each other this way, they would break away this way, okay? Just to preserve the symmetry here, symmetry of the angles and everything, right? So that's one of the things you need to remember. Just to show you another example that could happen. Imagine I have a situation, and don't worry, I would give you the exact example of this one later on. And if you go through my questions, you would see that this kind of example is there. So this is a very particular example, very nice example. So these are the open loop poles again, and you would see for this particular example that this pole is moving in this direction, this pole would be moving in this direction, okay, and this pole would be moving in this direction as I keep on increasing the value of gain k, and this pole would be moving in this direction, okay, and they all meet at the same point at the same value of gain k, right? And from there, so this is the breakaway point where you necessarily have this is the breakaway point where you have four roots meeting each other, right? And here the breakaway will happen this way, so that the angle so that the symmetry is preserved. So we are back again, right? And I'm really grateful for the outstanding service provided by my ISP. Seriously, I'm really grateful to my ISP for their outstanding service. In any case, so I don't know how much of the stream really went through before I was saying this, talking about this one. So this would be another example of a root locus where there are four poles here. So these are the open loop pole locations, right? These are the open loop pole locations. So these are at gain k equal to 0, and from there, as we increase the gain k, what happens? The four roots approach each other and they meet at a certain point. So this is kind of a breakaway point where there are four poles meeting each other, right? And then they would break away from each other like this with 45 degrees angle, right? So 45 degree here, 45 degree here, 45 here, 45 here. So something like that would happen. Again, there is one untold rule about root locus, is that root locus itself, the root locus cannot intersect each other. The root locus cannot intersect itself, rather. Okay, intersect itself. So that would kind of violate many things in algebra daily. Okay, so the root locus cannot intersect itself, right? So that is something you have to remember, and that is one of the reasons why this kind of breakage really happens. Okay, so just keep in mind, so breakaway points do happen this way, right? So the angle will be equally shared in a sense, right? But again, you have to understand that this is on a microscopic scale here. For example, so essentially look very carefully. If I go back to the original diagram here, the breakaway did really happen at 90 degrees, right? So it did break away, the poles did break away at 90-degree angles, and then the angle changed. So that could happen. But the point at which the breakaway happens, okay, should be shared, the angles should be shared equally. And this is again due to the angle criteria. Okay, this is pretty much due to the angle criteria. Okay. All right. With that said, so we have completed our discussion on breakaway points and break-in points. Now let's again for the moment go back to the original root locus, right? So we did see the root locus carefully. Right? So now we know, of course, by virtue of Rautharovitz on this, we know that when gain k becomes 60, the system becomes marginally stable, right? So we know that. We also, from the Raut table which we constructed at an earlier class, we know that when gain k is equal to 60 for this particular system, we have two poles on the j omega axis and one on the real axis, right? On the negative real axis, right? Someone is asking, yes, does that mean that there are no other possibilities for a breakaway and break-in point? Yeah, actually right. So if somehow the roots are meeting this way, so they would break away this way. Okay. Similarly, for break-in points, if the roots are meeting this way, okay, they would break in this way. So again, all these things are to preserve the other rules, right? So all the rules that you study in this one would be complementary to each other, right? And that way, if one of the rules are designed in a way that it violates the criteria, violates one of the other rules, it really wouldn't make any sense, right? And everything kind of builds upon either basic facts or on the other rules, right? And again, everything is designed to actually solve those two equations, right? The magnitude criteria and the angle criteria, right? Right. Similarly, if you have four roots meeting each other this way, then they would diverge this way. So that's one of the things you have to remember here, right? So as I was talking, say we know at gain k equal to 60, the roots diverge from each other. So the roots, two of the roots become complex conjugate pairs on the j omega axis, and one of the roots is real and on the negative half, left half plane. So of course one of that root is here when gain k equal to 60, maybe somewhere here, I don't know. When k equal to 60, maybe this root went up to this point, I don't know, something like that. This could have happened, right? And the other two roots are here and here on the j omega axis when k equal to 60, right? So that's easy to understand, I think. Okay, but you have to understand that something happens between when the gain was 0.385 and 60, right? So between gain k equal to 0.385 and 60, the roots took this path, right? The roots took this path, right? And one of them took this path, right? Something like that. So at any intermediate gain between 0.385 and 60, say for example, say take 40, right? When k is 40, one of the roots would be somewhere like here, one of the roots would be here, and the other might be like here, right? So we would have a complex conjugate pole pair on the left half plane and one pole on the real axis on the left half plane, right? So this would behave under this condition, the system would behave like an underdamped system, right? Essentially anywhere between k equal to 0.385 and k equal to 60, the system is an underdamped system, right? So we can say that, right, pretty easily, right? So we would have a complex conjugate pole pair on the left half plane that would make the system underdamped, right? So that way now we can say happily again, so we discussed all these things. Now let's put another thing here. Let's put another thing. We are saying right now that when gain k is greater than 0.385, hold on, when the gain k is greater than 0.385 and less than 60, okay, at 60 the system is marginally stable, and at 0.385 the system is critically damped, because there are 2 poles on the real axis and they are equal here, and marginally stable means undamped. So at k equal to 60 the system is undamped really. Okay, so with that said, we can say under this gain the system is underdamped really, because we have complex conjugate pole pair like that. Okay, so that would take precedence over this. So that way again just one more thing, I don't think I mentioned it. The closer the poles are to the right, so the poles that are so for example, just one important thing you need to remember. Okay, so if I have there is a certain idea of dominance of poles. So if I have poles here, 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 something like that, for example, for a system, these are more dominant than these. Okay, and this is more dominant than these. Okay, and you can let me know if you can figure this out. And if I have poles here, those will be more dominant than the rest of these. Okay, the poles towards the right on the S-plane have more dominance on the response of the system than those towards the left. Okay, and can you figure this condition out? Can you figure this out? And we shall talk about dominance later on. Okay, not right now. Just keep that in mind. So again, the idea is that if you have a pole pair on the geometric axis, then system becomes marginally stable. So the system becomes undamped, right? And wouldn't matter whether I have poles on the real axis, whether I have other poles here. Okay, their damping conditions wouldn't matter, right? And if I have poles on the geometric axis, the system will become undamped. Okay, so that way you can also think about this in a way, in a way that I have poles that are more dominant than the others. Right? So if I have a stable system, that if I have a marginally stable system, it would indicate that there are poles on the geometric axis, and those are going to be the rightmost poles for the system, and those would take precedence over everything else. So that's something you are going to automatically kind of have a feeling about as you go on with this course. But yes, so we can say that within this range of the damping ratio, so within this range of the forward path gain, the system is underdamped. Right? Now, what about this path? I mean, did I draw this line arbitrarily? I mean, did I draw this? So I knew, yeah, universal fact. So the question is, did I draw these lines arbitrarily, right? So I knew that this was the breakaway point, and I knew this was the breakaway point. I knew this was the breakaway point, and I also knew that these were the points at which they cross the geometric axis, right? I knew, kind of, right? So question is, I mean, did I just draw this arbitrarily? No, not really, right? So to figure that out, let's talk about our fourth rule. And again, the fourth rule wouldn't be anything new because you already know about this somehow. Okay, so rule number 4. And of course, you can figure the rule number 4 out yourself. So rule number 4, it's geometric axis crossing. Geometric axis crossing. Okay, I mean the condition and everything about the geometric axis, right? When it crosses the geometric axis. And now YouTube is saying something. It says the stream's current bit rate is higher than the recommended. Wow. Okay, I don't care. All right, geometric axis crossing. Okay, now of course, what was the transfer function we were dealing with? So for us, GS, we should really write GSHS, but for us, GS was essentially, let's write GSHS, the loop transfer function. Okay, let's just talk about the transfer function here, or rather maybe what was the characteristic equation? We did have the characteristic, we did write the characteristic equation, right? So this was the characteristic equation, right? Let's copy it. So this was the characteristic equation of the closed loop system, right? Let's copy this, and kind of this is the reason I am doing it on the same paper here. So we already have this, right? This was the characteristic equation, right? Rather, we are talking about the characteristic polynomial. This is the characteristic polynomial of the closed loop system. Of course, CL stands for closed loop system. Now let's construct the route table. We already are familiar with this. So let's construct the route table. So essentially, rule number 4 is nothing but applying route table on the problem of root locus. Okay, and we did. Okay, someone is saying please provide PID tuning videos using anaconda. Right. So just to address your question for a moment, please go to this. Hold on for a second. Please go to this link. Okay, so please go to this. Okay, this is the website for the Python's control system library. Please go to this first. Okay, there are plenty of things that you can learn here. Okay, and I'm pretty sure that your question can be answered here. Okay, all right. And if time permits, we are going to definitely talk about PID control and everything using Python, of course, right? All right. All right, so let's construct the route table here. So let's construct the route table. So we have an S cube row. This is kind of being redundant here. We actually did construct the route table for this transfer function, this system, right? So we have S square row, S to the power 1 row, and S to the power 0 row. And here we have 1, 11, 6, and we have k plus 6, right? And this is going to be 66 minus k minus 6, so 60 minus k divided by 6, and we have a 0. We could write it, we could skip it, whatever we want, and that's going to be k plus 6. And now, why are we just constructing another route table here? We are constructing the route table because we want to see the j omega axis crossing here, right? And really, this rule is not a rule, but a kind of a construction rule, how you are going to figure this thing out. So j omega axis crossing can be figured out by forcing a difficulty 2 in the route table. So now we are trying to force a difficulty 2 situation in our route table. We are kind of forcing a difficulty 2. And how can I force a difficulty 2? Just by making one of these at odd numbered power row here turn into 0, right? So I have to turn this into a 0. I have to make this a 0. And how can I do that? Of course, when k becomes 60, right? So I have to put k equal to 60, and that turns this into a difficulty 2 situation, right? And if this turns into a difficulty 2 situation, then this row in the route table actually provides me the auxiliary equation, right? Auxiliary polynomial, right? And auxiliary roots of the auxiliary polynomial are also roots of the actual original polynomial, right? So if k equal to 60, the auxiliary polynomial is this one, right? So that's going to be 60 s square plus k plus 6, and again k is 60, which is again so essentially this is 6 s square plus 66, right? And solving this auxiliary polynomial would give you the roots that are on the j omega axis, right? So the roots, again, we had elaborate discussion on this, so in our Raut Hurwitz classes, right? So I'm not going to discuss how that thing happens, but just so the roots on the j omega axis will be at the solution of this. So essentially, if I solve this now, so we know 6 s square plus 66 equal to 0. So the roots of this, okay, will be, so essentially this is like s square plus 11 equal to 0. So s equal to plus minus j root 11 will be at will be at plus minus j root 11, right? Plus minus j plus minus j root 11. Of course, these are purely imaginary numbers, right? So now let's go back to our plot original here. If I now look at the plot here, look very carefully. Previously we just mentioned that at gain k equal to 60 we would have two poles on the geometry axis, but we did not mention the exact locations at which they would cross the geometry axis from, right? So we did not exactly mention this particular location here. Now we are going to mention that. So we are now going to mention that at this point, essentially when k is equal to 60, they would cross the geometry axis, and the point here in particular, just a moment, should I put some space here? I think so. Okay, and the point here in particular would be, for example, this particular point here would be plus j root 11. Okay, and again this particular point here would be minus j root 11. And now let me bring my calculator up. And what is root 11? What is root 11? That's approximately 3.32, right? All right, so I can write down this to be minus j 3.32. all right, and that's of course again plus j 3.32. Of course the poles are on the geometric axis, so these are the complex conjugate pole pairs we were discussing, right? So that's how you figure out the imaginary axis crossing, right? That's how you figure out the gain and the point at which the root locus crosses the imaginary axis, right? And by crossing the imaginary axis, I mean the root locus automatically goes to the unstable portions of the S-plane, right? So the right half plane is unstable, left half plane is the stable portion, and the geometric axis is between stability and instability, right? So that is something we have. And again, there is something I should have written earlier. So k tends to infinity here. So again, if you have any difficulty understanding any of these, just drop your question here. All right, so that's rule number 4. That's nothing new. That is something you absolutely knew already, right? That's rule number 4. Okay, but there is something we have to discuss, and that point is that the picture I had drawn was wrong. You might say, what? Yes, the picture I have been using so far, or rather the picture in the very first page of my drawing here, is not really correct entirely. So this picture that you see, this root locus that you see, of course I drew it by hand, but I intentionally made it a wrong drawing, and you would know why exactly. Okay, so let's talk about that. I asked moments ago that I just had drawn a curve like that, so I knew this point to be true, I knew this point to be true, I knew the exact locations of the geometric axis crossing, and I have just made a arbitrary curve joining them, right? I made an arbitrary curve joining them, right? But could it not be something like this? I mean, what is stopping it from being a curve that looks like this, right? What is really stopping it from being? Of course, it has to be symmetric about the real axis. That part has to be true always. But what is really stopping it from being a root locus that kind of looks like this? What is really stopping it from being that? Well, is there anything that is stopping it from being a root locus that looks like this? Okay. So intentionally my drawing was wrong to make a point very clear. Don't ever take anything granted in engineering. Okay, it might seem pretty obvious that okay, we have 2 points, let's join them with a smooth curve. Why not a straight line, right? A straight line would be the simplest thing to join 2 points with, right? So we have 2 points, let's join them with a straight line, poor straight line. Make a nice straight line and join them by a straight line. Who cares? Yes, straight line is the easiest option, right? Why not join them with a straight line? Number one point would be that if I join them with a straight line, rule number 3 would be violated. And what does rule number 3 say? That whenever I break away, okay, the angle criteria must be preserved. So they should have really diverged. So if they break away at a straight line, and then this angle is no longer 90 degrees, right? So they are violating the condition of breakaway points. So that cannot happen. So they have to break away like this, right? They have to break away like this. So at the very verge of breakaway, they have to be like this. That is why they cannot cannot be joined with a straight line, right? But what about this kind of plots, right? So they did break away here with this absurd drawing here. They did break away at 90 degrees, right? So that breakaway condition is no longer violated. Okay. Also, this condition is not violated. So rule number 1 through 4 has not been violated if I draw this like this. Okay. But what about rule number 5, the next one? Let's talk about that. Right? And you will see why I had drawn it the way I did, and also the way I did was also wrong. Pretty weird, right? Okay. So by the end of this entire discussion, we're going to get rid of this entire drawing. Okay. By the end of this discussion, we're going to get rid of this drawing. Heck, let's get rid of this drawing right now, maybe. So that's one of the important things in life. Always ask questions. Never take anything for granted. Never ever take anything for granted, right? Okay, all right. So we kind of saw that it was breaking at 3.32. So let's point that out. If this distance is 1, I think I took a. Did I really though? Yes, I think I took the help of a graph paper. 1, 2, 3. So they would kind of break away at this. Not break away. They would kind of cross the geometric axis at this point. Okay, let's bring the graph paper. Okay, I brought the graph paper back. So I was really here, and so that was 4 spaces, right? So that would be this is like 1, this is like 2. Okay, okay, really speaking, this was a bad drawing from the get-go. This was a really bad drawing from the get-go, right? My bad. So let's dump the entire drawing, okay, and let's make a better one. We have all the information we need in your head, not in my head, of course. So let's get rid of these. Get rid of these. My axis should be proper, so that's one of the most important things here. And don't worry, I would have told you that during the exam you would get a graph paper to draw all these things, but unfortunately these exams are not going to be regular exams anymore, so I cannot tell you that you're going to get a graph paper. In any case, you understand the point. Okay, let's bring this and move this slightly. I don't know what I did. I'm afraid I have to get rid of this entire thing. Let's delete. So let's construct the entire root locus from the very beginning. Okay, that will be the nicest thing we can do. All right, let's waste time. All right. All right. So let's make sure that we draw it to scale. Unfortunately, in the previous drawing, it wasn't to scale, right? So that was the point 1. So that's 1. Sorry, that's -1. That's -2. You can watch me struggle with the drawing because this is really pretty difficult to draw here. And this is 1, on this axis, this is 2 on this axis, this is 3 on this axis. It was supposed to go beyond that, but unfortunately I made a poor drawing once again. Nice. That's all right. So we have 1, 2, 3, and that's gonna be 4. Nice. And here down below, this is 1. So that's 1, that's 2, that's 3, and that's 4. Nice again. All right. So now let's try to construct this the proper way. Okay. So we have let's see if I take a line. So we have the open loop pole here, here, and here. So these are the open loop poles that we have, right? And this open loop, so these poles were approaching each other this way. So this was approaching, let's use a different ink maybe. All right. So this was approaching this way. So these two are approaching each other, right? So in this direction. Okay. And this was going in this direction. Right? So this is at s equal to minus 3. This is at s equal to minus 2. This is at s equal to minus 1. Right? And these were at gain k equal to 0, k equal to 0, k equal to 0. And this is when k tends to infinity. Okay. We also know that at what was again at which they break away. What was the point at which they break away? That was minus 1.42 and the gain was 0.385. So 0.385 minus 1.42. So that's gonna be here really. Here is the breakaway point really. Really. I don't know, those of you who are attending this class through a phone might have difficulty in seeing this thing, right? So that is the breakaway point here really. All right, and from there the poles would break away. And let me just write it down maybe. Sure, why not? Okay. All right. Okay, so that's the breakaway point here. So that is happening at s equal to minus 1.42 and the gain at this point would be 0.385. Okay, let's use a different ink here maybe. I don't know. Different ink represent different things. All right, and what about the geometric axis crossing thing? We know that the geometric axis crossing happens at gain 60 and the points are what was the exact value? It was root over 11, right? So root over 11, 3.32 approximately. So that if that is 3, then it's gonna be this is 1, 2, 3. That is going to be approximately 3.32, halfway around here. And if this is 1, this is 2, this is 3, this is gonna be approximately 3.32, right? So I would say that these are those points essentially. Okay, so these are s equal to plus j root 11, so which is approximately plus j 3.32, and this happens at gain k equal to 60. And this is also the same thing here. So that's s equal to minus j root 11, so that approximately minus j 3.32, and that also happens at k equal to 60, of course, because of the symmetry here. Okay, so now I also know that the root locus would depart, root locus diverge from the breakaway point at 90-degree angles, right? So we know that, but we are not drawing it just yet. We are not drawing it just yet. So get rid of this space time. Okay, so we took our time to draw this properly. Okay, right, up to scale. This is now up to scale, right? No problem, right? All right, so with this let's now jump to our point number 5. Jump to our point number 5. Okay, so we have seen that, right? So now I said that, recall, these roots will have to start from here, right? These roots will have to start from here. These roots will have to start from here, and they have to diverge from each other at a 90-degree angle, but they have to cross this also, right? They have to cross over to to the right half plane from this, and also down below from this, right? But now question is, what kind of path would they follow? What kind of path would they follow, right? That idea actually comes from a slightly complicated understanding of root locus, or slightly more involved understanding of root locus, and let's talk about that. Rule number 5 talks about centroids and asymptotes. Centroid and asymptotes. Now, what are asymptotes? For us, the different definition of asymptotes are essentially tangents at infinity, right? So essentially, for example, if I draw a rectangular hyperbola, for example, then both the x-axis and the y-axis are asymptotes of the rectangular hyperbola, right? So if the equation is y equal to 1 by x, in that case both the x-axis and the y-axis are asymptotes. So asymptotes are essentially tangents at infinity. For example, here, if I go to infinity along the x-axis, then the x-axis itself becomes a tangent on this, okay? And if I go to infinity along the y-axis here, then the y-axis becomes a tangent of this curve. So essentially, for our intents and purposes, the oversimplified definition of an asymptote of a curve is a tangent on the curve at infinity, okay? Something like that, okay? So again, more usual examples would be, for example, if I say y equal to tan x, then you know that how the graph looks like, right? So for example, I'm only drawing it on the principal domain, for example. So that graph of the tangent kind of looks like this. Tan x kind of looks like this. Okay, and these lines that I can draw, so essentially at x equal to pi by 2, and in fact any odd multiple of pi by 2, they actually goes, this curve actually goes to infinity, right? Also at minus pi by 2, something like that. This is at minus pi by 2, this is at pi by 2. These are all asymptotes. So essentially I can say x equal to pi by 2, x equal to minus pi by 2, and so on, x equal to 3 pi by 2, 4 pi by 2, and so on. These are asymptotes of tan x, right? So essentially, if you draw them up to infinity along the y-axis, then these vertical lines are going to be tangents on them, and these tangents are not really tangents at a finite point, but tangents at infinity. So they are asymptotes of this curve, right? So again, this is something you have to understand, rather remember, I think. Okay, again, you studied this in your school, hopefully. All right, so now let's talk about centroids and asymptotes. Now we would say, if you recall the root locus, what was happening was that the roots were going to infinity, right? The roots were trying to go to infinity, right? Now when the roots are trying to go to infinity, then what happens is that I have to figure something out about infinity. Now thinking about infinity is a very difficult task, because we human beings are pretty finite beings, right? So thinking about infinity is pretty difficult, and as such we have to figure something out. What happens when the roots reach infinity, maybe, right? For what happens when very large gain appears, right? So I'm saying that the roots would appear go to infinity when the gain is infinity. For example, the gain is infinite. So now we are saying that instead of just arbitrarily drawing the curves when the gain goes to infinity, we are going to figure out certain things called asymptotes and make sure that we draw it a way that the curves follow the asymptotes, such that the asymptotes are tangents to those curves when the gain becomes infinity. Do you understand what I'm saying? I'm saying that when the gain becomes pretty large, then the curves essentially go to infinity. The root essentially go to infinity if there are no zeros. We shall later on see transfer functions that have finite zeros, finite open loop zeros, and for those situations the result would be slightly different, right? But for right now, we are going to only talk about transfer functions that do not have finite open loop zeros. For them, the roots would follow the asymptotes. Okay, so we are writing the rule here and explaining this. Okay, so we are saying that as k tends to infinity, the roots approach infinity along the asymptotes if there are finite open loop poles. If there are finite open loop poles, sorry, open loop zeros, then there would be poles that approach the open loop zeros as k tends to infinity. So there would be poles that approach the open loop poles at as k tends to infinity, and the rest would approach the asymptotes. Now, don't worry about the open loop zeros just yet, because I'm going to talk about that with proper transfer functions that have open loop zeros, finite open loop zeros, and we are going to figure out how those things work together, right? For the moment, try to figure out that when try to understand that when the gain becomes infinity, the roots would approach infinity as well, but along the asymptotes. But how do I construct the asymptotes? We construct the asymptotes through something called a centroid. So we are going to say that the asymptotes originate from the centroid, and unfortunately I cannot prove this to you right now, because in that case I would have to take the transfer function, put an infinite gain, and do a differentiation, partial differentiation, and show you the particular formula how it is derived, because that would take yet another class on this, right? So yes, so we're going to skip, again we're going to skip certain derivations here, but if you are interested I can give you the materials, or if you are interested I can arrange additional classes, but I cannot go through all the proofs and everything during our regular classes, unfortunately. So asymptotes originate from the centroid defined by this. There is one important thing to note, that the centroid is always going to be a real number. The centroid cannot be a complex number. Okay, and this is equal to, I'm writing this as this, summation poles minus summation zeros divided by number of poles minus number of zeros. Okay, so what does this mean? Let me just write it down. Summation pi equal to sum of all open loop poles summation zi is sum of all open loop zeros. P equals number of open loop poles. Z equals number of open loop zeros. And don't worry, when we have finished constructing all our rules, it will be pretty easy to construct the root locus of any given transfer function actually. Okay. Okay, right. So as we are given by this, and then we would say that there would be p minus z number of asymptotes sharing 360 degrees equally. Okay, equally. And instead of saying that, let's just write down the angles. Okay, it's going to be divide 360. So that way, that's going to be 20. Hold on a second, 240. How do I write that? Instead of saying this, let's asymptotes equally, asymptotes with angles. Let's just write that with angles 2n plus 1 divided by p minus z times 180. In this case it's going to be 30, and this is going to be 2n minus 1, right? So that's going to be 60, 180. Right, no problem. Okay, it'll be pretty evident what I mean here, right? Okay, just keep this entire story here. So look at the transfer function. What was the transfer function here? What was the open loop transfer function? Our open loop transfer function was here was GSHS. Again, HS is 1, so don't worry about that. So it was 1 divided by S plus 1, S plus 2, S plus 3. And the open loop, so it had 0 open loop zeros, right? So I'm saying right off the bat, I'm saying P is 3. So number of open loop poles is 3. Number of open loop zeros is 0. So there are no finite open loop zeros here, right? And what are the pole locations? So I'm saying Pi are the pole locations. Here these are at -1, -2 and -3. And what are Zi? Zi are not there. Since there are no finite open loop zeros, there are not these things. So what is the centroid? What is the centroid's location? So the centroid's location is essentially summation Pi minus summation Zi divided by P minus Z, right? So, and if you calculate this, this becomes -1, -2, -3, sum of all the poles, -0, nothing there, okay, for the zeros, and number of open loop poles minus number of open loop zeros. So that's going to be 3 minus 0, right? Now if you calculate this, this becomes -6 divided by 3. So that's -6 divided by 3, that gives you -2. So location of the centroid. Someone saying, so for n equal to 0 the angle would be negative. No. Oh, something I just missed. Unfortunately there is something I missed. I missed to write this. N has to be 1, 2, 3 and so on up to P minus Z. So if you have 3 poles in the 3 asymptotes, in that case N would be 1, 2 and 3. Okay, all right. So that's the centroid's location. Okay, that's the centroid location, and figure out the angles of the asymptotes. So we know that there will be 3 asymptotes and the angles of the asymptotes. So there, how many asymptotes would there be? That's, again, p minus z is equal to 3. Therefore, there would be 3 asymptotes. There will be 3 asymptotes, and the angles, yes. So your questions are pretty amazing in the sense that you're actually following properly, right? So when I wrote this equation without actually pointing out the values of n, you figured out promptly that it could give you a negative angle, right? So yes, that kind of confirmation is pretty nice. So, and the angles of the asymptotes would be, so we know that the angles would be 2n minus 1 times 180 degree divided by p minus z. So that's total number of open loop poles minus total, so that's 3 here. So here the angles are for n equal to 1, so that's one of the angles. Then the other would be 2 times 2 minus 1 times 180 degree divided by 3, and the last one would be 2 times 2 minus 1 times 180 degrees divided by 3, or so this is 60 degrees. This is how much? 60 times 3, that's 180 degrees, and this is how much? Sorry, this is going to be 3, right? 2 times 3, so this is 300 degrees. So I would have 3 asymptotes with these angles, right? And the asymptotes would originate at sigma equal to minus 2. So let's go back to the drawing. Okay, let's get back to the drawing. Okay, so let's just also mark the axes properly. So this is 0, this is 1, this is 2, this is 3, of course on the geometry axis, this is 4, that's minus 1, minus 2, minus 3, minus 4. All right, so that's fine, I think. Nice. So I'm saying that the asymptotes would originate at s equal to minus 2. Now this is kind of a fortunate thing or unfortunate thing, depends on how you are looking into it, but keep in mind that if the asymptotes are originating from s equal to minus 2, essentially the asymptotes are originating from here, right? So asymptotes are originating from this point, right? From this very location of the pole. Now this might not happen. This it might so happen that the asymptotes are originating from any other possible angle, right? It might so happen that the asymptotes are originating from any other possible angle, right? A possible centroid location. But this is also the location of the centroid. So just keep in mind, and let me just mark this point by saying that this is the origin of the asymptotes. This is also where the asymptotes originate from. So this is where the asymptotes originate from. This is the centroid. This is also the centroid. Sigma equals minus 2, right? Now we have to draw 3 asymptotes. So asymptotes are tangents at infinity again. Okay, and now these tangents are essentially straight lines. They originate from this point, so we know their origin, and we also know their angles, right? So one of them is at 60 degree, the other is at 300 degree, but 300 degree is nothing but minus 60 degree, right? So if this one goes in this direction, the other one would go in this direction, right? Essentially, and the other one is 180 degrees, so essentially in this direction, right? So we have 3 asymptotes like that, right? But we have to now properly construct 60 degrees. We could do that if we have something like a protractor or something, okay? But if we don't worry, we have our trusty calculator, right? So we have to draw a line. We have to draw a line like that, asymptote starting from this, that makes a 60 degree angle. How can I do that without a protractor? We can pretty easily do that by using a little bit of trigonometry here. What kind of trigonometry? Pretty easy trigonometry. Let's see. We know this distance, right? So for example, you try to understand. Look at this length. What is this length? What is this length? This length is 2. of course, because this pole is at -2, so this length is 2. This centroid is at -2, so this length is 2, right? And I want to draw a curve, draw a straight line that makes a 60-degree angle here. So if this length is 2 and this is 60-degree, right? So how much length is this one? How much length is this one? This perpendicular here. So that's 2 tan 60-degree, right? 2 tangent 60-degree. So 2 tan 60-degree, right? So a little bit of trigonometry. So this vertical length would be 60-degree, 2 tan 60-degree. But tan 60-degree is √3. So 2 √3. What is 2 √3? So that's 2 times 1.732, right? So that's, I can do this calculation by myself. That's going to be 463.4. So that's going to be 3.464, rather 3.46, I think. 3.46. So with all these, I can now do something pretty useful. So we know the points would start from here. Now we are going to mark this point 3.46 here. We are going to mark this point 3.46 here. And now if I take this and draw a line that starts from here and goes like this, that would pretty much be an angle, pretty much be a straight line that starts at the centroid and makes a 60-degree angle with the positive real axis. All right. So we made use of geometry. Pretty useful in that sense. So let's instead take a thinner line with a different color of ink here. Maybe let's take orange. Right. So that's one of your asymptotes. Right. So that's making 60 degrees. Right. So that's one of your asymptotes. Right. And we have to do the same thing here. So this point is somewhere going to be like this, and that's going to be 300 degree or minus 60 degree essentially for all intents and purposes. Hold on for a second. Again, the root locus is going to be symmetric about the real axis. So asymptotes are also symmetric about the real axis, right? Because of the very idea that we have a polynomial with real coefficients. And other asymptotes is the other one is here, but it's barely visible, unfortunately. It's hardly visible, unfortunately. So let's make this visible. It's hardly visible, so let's make this visible forcefully. Alright, so this is one of the asymptotes, right? So these are the three asymptotes. So look very carefully. This is making an angle of 60 degree. So this asymptote is making an angle of 60 degree. This is making an angle of minus 60 degree, which is 300 degree if you look in the counterclockwise direction. And this asymptote, which is again originating from this, is 180 degrees. So these are the three asymptotes. Right? So these are the three asymptotes. So we have successfully done drawing our asymptotes, right? So again, let's do that. Let's put a legend here saying that these lines that are drawn with this particular color are the asymptotes. All right. So these are the asymptotes. And now we also confirmed by our theory that the asymptotes are tangents at infinity for the root loci. So essentially, the roots would follow the asymptotes. So again, already one of the roots is already following the asymptotes, right? Asymptote. So this asymptote, say, let's say this is asymptote number 1, this is asymptote number 2, and say this is asymptote number 3. And we can say already this root, that was this pole, that was at s equal to -3, as gain increased, this root already is following the asymptote number 2. And the other two roots, after breaking away from this breakaway point, should also follow the asymptotes. So this is how I'm going to draw the rest of it. I am going to draw I'm going to make sure that the rule number 3 is not violated. So when it breaks away at an angle of 90 degrees from both sides, so plus minus 90 degrees, so like that. And after so this is going to be a very difficult drawing for me because of the way I'm drawing with the Wacom tablet and everything, right? So this is going to break away from this point at 90 degrees, and then unfortunately the shape recognition would take over. This is becoming very, very difficult for me. And then they would try to follow along the asymptotes. This is becoming ridiculous. Let me try my best to draw this. Okay. I really don't struggle this much while doing this on a paper. And also on your board. But really I want this to be perfect, and that is why I'm struggling this much. No, poor drawing. Really poor drawing once again. I don't think this kind of drawing would suffice. You can understand the struggle of teaching this kind of things in online mode, right? Am I right? Nice. So let's make this a thicker one. Practice makes people perfect, right? So I am someone who is trying to be perfect at this point, but I might just well give up. This is one of the shortcomings of this particular Wacom tablet, actually, unfortunately. Yes, so when you are unable, just blame the tools, right? But yes, truly this is one of the shortcomings here. This is called pen jitter. Basically if I move very slowly, then there is something called a jitter, pen jitter, which happens really. Right, it is more or less presentable, whatever it is, right? Nice. I think I knew this was going to give me a lot of trouble. All right, so now we have a better drawing. Just keep in mind that the previous drawing that I had, I said the curve was not right because of this, because in the last one I had drawn this way, right? We had two poles, they are meeting each other, and then I had drawn them like part of circles or something like that. No, they have to follow the asymptotes, and the asymptotes have to be their tangents, right? So now look very carefully. They are crossing over the j omega axis at those precisely defined points defined by rule number 4. Okay, and they are following the asymptotes as per the rule number 5. All right, and essentially here I can write that this is k tending to infinity. So when k tends to infinity, the root locus also goes to infinity. So I can happily put arrows here indicating that the roots are traveling this way. So what have we figured out so far? So this is the end of this particular root locus, but we have so far only gathered 5 rules, but there are, I told you earlier, there are exactly 10 rules about root locus. So we haven't yet studied quite a few. Okay, essentially we haven't yet encountered quite a few, right? All right, so with that said, let's think about what we have learned so far, right? So we have learned so far that when the root locus starts at k equal to 0, the root locus starts at the locations of the open loop poles, and as the gain increases and becomes very large, the root locus either ends at open loop poles, root locus starts at open loop poles, and as the gain increases, the root locus either ends at open loop zeros or goes to infinity along the asymptotes, right? Along the asymptotes. So here the things that we have discovered so far are that for at k equal to 0, the root locus, rather root loci, start at the open loop poles. Number 2, we have learned that apart from the rules what we have discovered here, so as k tends to infinity, the roots go to the open loop poles, open loop zeros, rather instead of saying go to, roots approach, I would say, because you can never go to infinity, you can only approach infinity. So the roots approach the open loop zeros, and the rest follows the asymptotes, right? So these are things we have figured out, but in this particular case we have figured out that that as long as the gain k is between 0 is gain k is greater than 0 and less than 0.385, the system was over damped, because we had real and unequal roots, right? So we had real roots and unequal roots. Then we figured out at exactly k equal to 0.385, we would have 2 equal and real roots here to the right, so it would be critically damped. Then we figured out when the gain was greater than 0.385 but less than 60, we had complex conjugate pole pairs, so the poles were like this, right? Complex conjugate pole pairs. So I would say the system is under damped. And then afterwards, when k is exactly equal to 60, there are 2 poles on the j omega axis, so system is undamped. Okay, so undamped also means marginally stable. Just one more thing, also keep in mind that if I have 2 poles on the j omega axis but I have a pole here maybe, then there is no point of saying undamped or anything, it's unstable, right? So the poles on the rightmost poles take precedence when talking about how the damping is. Okay, so the rightmost poles would take precedence here. And also when k is beyond 60, the system is unstable. we can see that these two poles, when k is beyond 60, these two poles would go to the right half plane and approach infinity from there. So these are the practical things we discovered about this particular system. All right. So again, just to say that this system was this particular one. So again, this was 1. Okay. Again, and this is R. This is. So we constructed the root locus of this. Okay. All right. So any question with this? All right. So if it is fine, so let's move into another problem here, and there we are going to figure out something else. Okay. Okay. We essentially are going to look into rule number 6, and for that particular rule number 6, we are going to look into another problem. All right. So again, if you have any query regarding this particular problem, please feel free to ask. All right. Since you don't have any more questions, so let's proceed to the next one. So let's take another example. Okay. And that would let us introduce rule number 6. Okay. Let's take another example. All right. So let's take this system, which kind of looks like this. Again, we have a forward path gain. We could have just given you the transfer function. I'm just drawing it for the sake of some sort of completeness here. Let me think about it, how I'm going to pose this problem. Right, no problem. So this is fine. It's a very simple second order system. Again, unity negative feedback, so don't worry about the feedback transfer function yet. All right, so let's take this example now. All right, so our transfer function gs, hs and whatever k. So again, if I write down the closed loop transfer function, so which is cs by rs, so that's going to be this whole thing here. So this is going to be k s plus 2 divided by s times s plus 1 whole divided by 1 plus k s plus 2 divided by s plus, sorry, s times s plus 1, right? And if you just do the simplification, this eventually becomes k times s plus 2 divided by s times s plus 1 plus k times s plus 2. So again, that's your closed loop transfer function, right, for this particular system, right? There is no problem in that, right? Now we can proceed with the standard way of dealing with it, like the way we approached the previous problem. But here, now we're going to apply the rules that we have learned so far, right? Apply the rules that we have learned so far. We know that the closed loop transfer function is nothing but this k, gs, hs. I'm writing k in particular here to make sure that you understand that the k is separate from g. But if I give you the transfer function along with the k, you have to make sure that to include the k, right? Sometimes in exams or sometimes in real life, people would write the k alongside the transfer function, right? So you would encounter this transfer function as such: k times s plus 2 divided by s times s plus 1, something like that. So you have to understand that the k is included there. In that case, you do not really necessarily separately include the k. Other than that, so kgs here, and here it's gonna be k gs hs, right? All right, so again, if you have any query, just let me just refresh the screen here. All right, so we have this, right? And we know the characteristic equation looks like this. So the characteristic equation is essentially the equation in the denominator. So 1 plus k gs hs is equal to 0, right? So we have, again, we talked about this in the last class, right? That's equal to -1, and that gives me k gs hs is equal to -1 by k, and that leads to two equations, namely the magnitude criteria and the angle criteria. And the magnitude criteria states that magnitude of gs hs should be equal to 1 by k, and the angle of gs hs should be equal to an odd multiple of pi. So essentially 2n plus 1 times pi, anything, and n could be positive, negative, or 0, any integer. Okay, so here these are the two criteria that actually turns out to be this, right? So again, we are dealing with GSHS, right? So this GSHS is called the loop transfer function. It is called the loop transfer function, and this is the important thing here to note, because in root locus technique, we're actually looking into the loop transfer function. Look very carefully. Okay, so basically we are solving for this, okay, where gs and hs are multiplied here. So loop transfer function, right? Often also called the open loop transfer function sometimes. Just keep this in mind. So in our example here, gshs is s plus 2 divided by s times s plus 1, right? So let's start with our rule number 1. And rule number 1 essentially is the rule that you have to keep in mind all the time, right? Other than that, let's use a graph paper. Let's change this page to a graph paper. All right, and let's bring our beautiful axes, right? All right, if it doesn't work, we have to remove everything and do over. All right, so now let's start with the open loop poles. Okay, where are the open loop poles? Open loop poles are at s equal to 0 and s equal to -1. So right off the bat, let's say what are the number of open loop poles? Open loop poles, how many open loop poles are there? There are 2 open loop poles. How many open loop zeros are there? there is one open loop 0, and the poles are at 0, -1, and the zeros are at -2, right? So right at the very beginning, let's denote the open loop poles and open loop zeros. So I am going to denote the open loop poles here. The open loop poles are at 0 and -1. So here is one open loop pole, here is another open loop pole, and there is an open loop 0 here, right? And this open loop 0 will be denoted with an O, right? So zeros on a pole 0 map is denoted with O, and poles are denoted with X. All right, that's pretty nice, I think. So again, this is, let's mark our axes properly. Let's take some space here because we might need it later on. Okay, so let's mark our axes properly. So here, this is going to be 1, this is 2, that's fine. Let's say this is 3. Nothing is there yet, but let's say this is 4. So that's 1 minus 2, that's 2. So this is 1, that's 2 here, and this is 1 here, and 2 here, that's 1, 2, so that's 0 again. So -1, 2. All right, and this is -1. So let's just write it out. So again, the root locus would start from these 2 points, right? So originally the root locus would be starting from this point. So when k is equal to 0, the roots are these, right? When k is equal to 0, the roots are these, right? So now let's do that and get rid of the page. Okay, so let's look at the characteristic equation first. Okay, so let's look at the characteristic equation. So what is the characteristic equation here? So the characteristic equation here for this one is s times s plus 1 plus k times s plus 2. So s times s plus 1 plus k times s plus 2, and that's equal to 0, right? Right. Now let's see, when k is equal to 0, what are the solutions? What are the closed loop poles? So if I solve this for different values of k, I get the closed loop poles, right? So when k is equal to 0, we are essentially solving for s times s plus 1 equal to 0, which gives me the solutions to be 0 and -1, which are the open loop poles. Right? So which are the open loop poles? So essentially the root locus starts from the open loop poles as usual. But other thing to note here is that when k approaches a very large value, when k approaches infinity, what are the solutions? When k approaches infinity, what are the solutions? Right? How do I see that? When k approaches infinity, how do I find out the solutions here? We find out the solution by dividing everything with k. So if I do that, then I essentially have s times s plus 1 divided by k plus s plus 2. Okay, and this is equal to 0 divided by k, but since k is a large quantity, this still remains 0. But this now becomes 0 because this is a finite quantity divided by k, so that becomes 0. So we have solutions that looks like this: s equal to -1, -2. So we get that when k tends to infinity, one of the roots is going to be -2. So, but this is the open loop 0. See, the open loop 0 at s equal to -2. So we can say when the gain approaches infinity, one of the roots of the closed loop system approaches the open loop 0. So this is the open loop 0, and one of the roots would be approaching the open loop 0, the location of the open loop 0, when the gain approaches infinity, right? So just keep that in mind. So these are the two locations. So s equal to -1 and s equal to 0 are the two locations from which the root locus starts. Okay, so now let's construct the root locus through the different rules that we studied earlier. All right, so now let's talk about the rule number 2. The rule number 2 gives me explicitly the locations on the real axis that are part of the root locus, right? So question is this part of the root locus on the real axis? is what am I saying? Is this part of the root real axis on the root locus? Answer is no. Of course, if I am standing here like a stick figure and looking to my right, I don't see anything. I don't see anything. So which means there are zero number of poles and zeros to my right. So that angle contribution is 0. And since the angle contribution is 0, I see that it cannot be an odd multiple of 180 degrees. So the angle criteria would be violated, right? So rule number 3 essentially tells you that those portions of the real line are on the root locus for which towards right you have odd number of poles and zeros together, right? So this part on the real axis is never going to be on the root locus here, right? With that said, question is this line on the real axis on the root locus? So is this part of the real axis on the root locus? Answer is yes, because if I'm standing here, look to the right, I have one pole to my right. It's part of the root locus. Question is this part on the root locus? The answer is no, because if I'm standing anywhere here, look to my right, there are two poles, not part of the root locus. Is this part on the root locus? The answer is yes, because if I stand on this part and look to my right, then I would see total 3 number of poles and zeros to my right. So essentially I have an odd angle contribution here and done, right? So this part is going to be on the root locus. So we have done this, but I haven't yet put any arrow, right? But you can imagine the direction of the arrows yourself. You can figure out the direction of the arrows. So essentially you can understand that this pole is approaching this one and this pole is approaching this one, right? This pole is approaching this one and this pole is approaching this one, and they would meet, of course, at a certain point, right? That has to happen, right? There is no other way than this this path can be on the root locus, right? There is no other way that this path can be on the root locus, right? Obvious, quite obvious, because the root locus cannot intersect itself. Now let's go to the rule number 3. Talk about the breakaway point and the break-in points, maybe. Okay, so let's just demark all the points. So this is this is -1, this is -2, that's -3, -4, and so on, right? So now think about this. So they are going to break away at a certain point, right? Let's think about that. And let's calculate the breakaway and break-in points. So we have already applied rule number 1. We have already applied rule number 1, rule number 2, and let's apply rule number 3. So let's start with the breakaway and break-in points. Let's talk about that. So we know that we have to look at the characteristic polynomial. So this is the characteristic polynomial. So if I write that, so this is again, let's just copy. Instead of writing this, let's just copy this. Okay, and we have to express this as, and of course this is equal to 0, right? And we have to express this as a function of k. So k is equal to minus s times s plus 1 divided by s plus 2. And when there are multiple roots on the then this is 0, right? Then so at breakaway or break-in points, del k del s is going to be 0, right? Thus, what is del k del s? So minus del s of this entire thing, s times s plus 1 divided by s plus 2, has to be 0, right? At the breakaway and break-in points. So if I differentiate this becomes s plus 2 whole square and s plus 2 and derivative of this, so that's going to give me 2s plus 1 and minus s times s plus 1, and derivative of the denominator, that gives me 1. So that has to be 0. Forget the denominator, that's non-zero, I'm assuming. And if that's non-zero, I'm assuming, then this is going to be 0. So I have s plus 2 times 2s plus 1 minus s times s plus 1, that's equal to 0. So let's solve for this, and if I get proper solutions, then those are going to be breakaway and break-in points. So this is going to be 2s square plus 4s plus 5. So 5s, so 4s, and so this is going to be 2 minus s square minus s equal to 0. Please do this calculation independent of me, because I can make mistakes in calculations. That's what I do. S square plus 4s plus 2, I think that's equal to 0. Let's solve for this, right? So the solutions are, so the possible, so let's just do that. So s here is equal to minus b. Oh, someone is saying there was a minus sign. I just got rid of the minus sign by multiplying it with a minus sign from both sides. Because we are solving for this, right? Minus b plus minus root over b square minus 4ac, 16 minus so 8 divided by 2a, so that's 2. All right, so these are at minus 2 plus minus, so I'm dividing, so this is 8 root 8, so root 8 means 2 root 2, and so that's going to be root 2. So minus 2 plus minus root 2, right? So what are the points? So I already know 3.414 would be one of them, because minus 2 minus 1.414, that's root 2. And what about the other one? Minus 2, let's bring up a calculator. What about the other one? That's minus 2 plus 1.414. That's 0.586. Right about it. That's minus 0.586. All right, so these are the two possible locations of breakaway and break-in points, and whether or not they are valid or invalid, that entirely depends on whether they are satisfying the angle criteria or not, right? Let's see whether they are satisfying the angle criteria or not. Let's look at this point, minus 3.414 is, so again value of s. So can this be a valid breakaway or break-in point? Minus 3.414. So let's look at this. Minus 3.414, where will it lie? Where is it going to be? Minus 3.414. So that's going to be somewhere here. Question is this a valid breakaway or break-in point? Fortunately for us, the answer is yes. This is going to be a valid breakaway or break-in point, because it is lying on a part of the real axis that is on the root locus, right? This entire part of the root locus, this entire part of the real axis is on the root locus. We already verified that by using rule number 2. And if my breakaway or break-in point is standing here, then definitely it is part of a, definitely it's a valid breakaway or break-in point. It's definitely a valid point, right? So this is a valid point, and let's mark this then. Let's mark that point. We know that this point is at minus 3.414. I don't yet know that whether it is going to be a break-in point or a break-away point, but it is a valid point nonetheless. And what about the other point? It is minus. It is at minus 0.586. Where is minus 0.586? Okay, minus 0.586 is going to be here. Question is this a valid point? The answer is once again yes. This is once again a valid point, and because of the very reason that it's on the real axis, and it's on such a part of the real axis which is inside the root locus, and as such this is not violating the angle criteria. So this is also a valid breakaway or break-in point, and as such let's mark this point. Let's say this is at s equal to minus 0.586, right? What was it? 0.586. 0.586. Now, which one of these do you think is a breakaway point, and which one of these do you think is a break-in point? I would let you guess. So this is point A and this is point B. Which one of these do you think is a breakaway point? Which one of these do you think is a break-in point? And of course, we are going to mathematically figure out which one of these is a breakaway point and which one of these is a break-in point. But I am letting you guess. Please guess. I'm coming back. So it makes me really happy to see that you have guessed it correctly. Nice. Right? So you have guessed it correctly, but let's do it mathematically, right? Let's try to understand how these things work. So how am I going to figure out which one of these is a breakaway point and which one of these is a break-in point? So let's do this mathematically, right? All right. So, and how am I going to approach that problem? It's pretty easy to approach it really. So let's look into that. So we confirm their validity by angle criteria. Now we are going to use the magnitude criteria, right? So these two are both valid breakaway or break-in points. So these two rather are both valid breakaway or break-in points. Now figure out which one of these is a breakaway and which one of these is a break-in point. Now let's check that using the magnitude criteria, right? So magnitude criteria tells me that this has to be true. Where is it? Yeah, magnitude criteria tells me that this has to be true, right? So that is the magnitude criteria, and for this particular scenario, this is s plus 2 divided by s times s plus 1. The mod of that will have to be 1 by k. So we are looking for the value of k, right? So what is the value of k? Value of k is then mod of s times s plus 1 divided by s plus 2. I don't think there is any issue, right? Now let's calculate the magnitude for different values of gain, different values of s, right? So let's calculate what is the gain. What is the gain when s is minus 0.586, when s is minus 0.586, and also let's calculate the gain, required gain to reach that point when s, same thing, do the same calculation when s is at minus 3.414. So let's put these values here and calculate the corresponding gain. So gain at this breakaway or break-in point and gain at this breakaway or break-in point. So this is either a breakaway or break-in point, this is either a breakaway or break-in point, valid points. Let's calculate the gains at those 2 points. Let's calculate those. Implies k equal to how much and implies k equal to how much. So k equal to how much. So I am leaving it to you. Or should I do the calculation myself? Let me do it myself, and you're going to verify my calculation, right? So minus 0.586. Let's bring up a calculator. I really would like to do it using Python, because that's a much better calculator, right? Honestly speaking, this calculation can be done pretty easily, but I like to do it the hard way somehow. So let's define so for example, what should I say, define k. Okay, it's a function of s, and it returns how much is it, absolute value of s times s plus 1 divided by s plus 2. S plus s times s plus 1 divided by s plus 2. So I would call the value of k for minus 0.586. All right, that's 0.17. How much is it? 0.172. No minus sign. There is a mod. 0.172. There is a mod on the whole thing, and the other one would be, okay, and the other one would be, I'm calculating k at minus 3.414, would be 5.83. Let's take the 3 digits. 5.828. 5.828. Just verify these calculations are okay. Okay. So that's the thing. I do write Python programs for even the tiniest things. All right. So here s is equal to minus 0.586, and here s is equal to minus 3.414. Now, which one of these do you think happens first? Okay. So again, the idea is that I am increasing the value of gain k starting from 0 and going up to infinity. So which one of these happens first? Of course, this one happens first, right? So this one happens first. This one happens first, and this one happens next. So this one happens first because this has a smaller gain, of course, and this has a higher gain. So if I keep on increasing the value of the gain starting from 0, then of course I would encounter this first, and then this one, right? So I would encounter this one first. But let's go to the picture again. Once again, the value of s here is minus 0.586. Let's go to the picture. I see minus s equal to minus 0.586 here, and subsequently the corresponding gain is 0. What did I write? 172, 0.172, and here I encountered the gain 5.828. So of course this is going to happen first, and this is going to happen next. So these poles are going to break away from here. So this point is the breakaway point. So the poles are going to break away from here, and then they are going to meet here. So they are going to meet here at point A, and from there they're going to break away. And then after that, when the gain has increased to 5.828, they are going to meet at minus 3.414. So this is going to be a break-in point. Okay, so this is going to be a breakaway point, and point B is going to be a break-in point. So break-in can only happen with poles that have broken away first. So the poles have to break away first, then they can meet later on, and that will result into a break-in. Okay, So that's a break-in point. So B is a break-in point, A is a breakaway point. All right. So we understand that already. Nice. Nice. So we haven't yet completely used up our rule number 3. There is one more thing we have to understand about rule number 3. The angle of breakaway and break-in. Here, the angle at which the poles would break away would be 90 degree here, 90 degree here, infinitesimally. So the very angle at which the breakaway happens would be 90 degree. And the very angle at which the break-in happens would be also 90 degree. Right? Something like that is going to happen. Right? So they are going to break in at 90, break away at 90 degrees. And also break in at 90 degrees. So that's going to be true here. So we have to keep that in mind, right? So we understand that. Now obviously, this pole that broke away from here is going to approach to this somehow. And this pole that has broken away from this is going to approach to this somehow. There is no other possible construction of the root locus, right? But to ensure that there is no other possible construction of the root locus, let's figure out the j omega axis crossing. Okay, let's figure out the j omega axis crossing, right? By using rule number 4, right? So let's apply j omega axis crossing rule. So this is a breakaway point. So this is breakaway, and this is break in. Okay, let's apply rule number 4. So j omega axis crossing. I would write possible j omega axis crossing. And instead of spending time on this, I'm leaving this as a homework. Construct the route table. You would see you will not be able to force a difficulty 2 situation on the route table. Okay, construct the route table with this characteristic polynomial. You already have the characteristic polynomial. This is the characteristic polynomial. Construct a route table with that, and you would see that you would be unable to force a difficulty 2 situation whatsoever. So the j omega axis crossing will never happen. And not only that, you won't even be able to force a instability on this. The system will always be stable as long as k is positive, and of course k is positive. So make sure to verify that using the route table. So rule number 4, if you apply it, you will see that the system can never be unstable, and also you can never force a difficulty 2 situation. You would see. Just verify that yourself, right? So with that verification, you would see that of course the poles cannot go to the other side, right? Go to the other side. So they have literally nowhere to go. What about the asymptotes? Let's think about the asymptotes. Right? How many asymptotes am I going to have? First question, how many? The answer is number of poles minus number of zeros. But how many open loop poles do I have? I have 2. And how many open loop zeros do I have? I have 1. So that's going to be 2 minus 1. So I have only one asymptote, right? What is the centroid? Centroid is at sigma equal to summation poles minus summation open loop zeros divided by number of poles minus number of zeros. But what is the summation of open loop poles? We know that the open loop poles are at 0 and minus 1. Open loop 0 is at minus 2. So this is going to be minus 1 minus of minus 2 divided by 1. So that's minus 1 minus of minus 2 divided by 1. So that's going to be 2 by 1. So that's just 1. So the centroid is at 1. And what is the angle of the asymptote here? Angle of the asymptote. So I have one asymptote and the centroid, one asymptote originating from sigma equal to 1. Okay. And the angle of the asymptote, just one asymptote, right? And we know that's going to be 2n minus 1 divided by p minus z, which is 1, times 180 degree. And here n is equal to 1. So put n equal to 1. So that's just 180 degree. So now what does it mean? So we have just one asymptote originating from s equal to 1. Oh, sorry, really. Yeah, originating from s equal to 1 and and with an angle of 180 degrees. What does that mean? It means that if I draw the asymptote, it is going to look somewhat like this. So asymptote would originate from somewhere here. So positive 1 here. Okay, plus 1. So asymptote would originate from here, and the asymptote would have an angle of 180 degrees. So the asymptote would be in that direction, right? The asymptote would be in that direction. So let's take a thinner line. So that's going to be the asymptote, direction of the asymptote, right? So there is just one asymptote in this direction like that. And with that said, if I say this is the direction of the asymptote, again this is the asymptote. Okay, so one of the poles must follow the asymptote, because I have one asymptote, so one of the poles must follow the asymptote. And of course I don't know what I'm going to do right now, because I don't have a pole that really follows the asymptote. Let's see what I can do, what we eventually figure out. Let's see. Okay, so we know that there is a breakaway point here and there is a breaking point here. So the poles would break away from here and approach this, and poles would break away from here and approach this. But what about when the poles are here midway, right, between the breakaway and breaking point? What about that? Now we have rule number 6. So rule number 6. Now existence of, now instead of spoiling the fun, let's figure that out. So let's figure this thing out ourselves. Now here within these 2 points, okay, keep in mind, while the roots are here, right, so this would break away and approach something like this here, and these roots will break away, this pole will break away and approach something like this. While they are here, they are complex conjugate pole pairs, right? They are complex conjugate pole pairs. So I can write them as sigma plus j omega, right? Complex conjugate pole pairs while they are here within that. And these are again supposed to be satisfying the angle criteria and the magnitude criteria. But let's just look at the angle criteria, right? Let us just look at the angle criteria. So I have the angle criteria, but the angle criteria says that the angle of GSHS must be an odd multiple of pi. Okay, odd multiple of pi. Again, n is a member of Zallen. Zallen is the all the integers, negative, positive, including 0, right? So any odd multiple of pi would do, right? So it implies that the angle of the whole transfer function, which is s plus 2 divided by s plus was s times s plus 1, that has to be an odd multiple of 2n plus 1 times pi, right? So that has to be 2n plus 1 plus pi, and later on we're just going to land up with a particular value of n here. But just for the moment, let's write down, this is angle s plus 2, again complex number, minus angle of s minus angle of s plus 2, because for complex numbers, you know, arg z1 divided by z2 z3 is just arg z1 minus arg z2 minus arg z3. Again, we have to add some pi to make the principal values properly merge, but yeah, just keep in mind that that principal value thing has been taken care of by this n. Okay, there are so many things in complex analysis that we are kind of sort of assuming to be true here. Okay, now since I know for sure that these poles are here, these particular roots are complex conjugate pairs, then I can simply write s equal to sigma plus j omega, right? So this is angle of sigma plus j omega plus 2 minus this is angle of sigma plus j omega, and this is angle of sigma plus j omega plus what did I write? That's gonna be 1, right? But no one pointed that out, so maybe you are not following properly. And that's going to be 2n plus 1 times pi. That has to be true, right? Again, very soon we're going to settle with a particular value of n here. Yes, you pointed out. Thanks. Now, what about this? Let me just again write it down as this is again angle of sigma plus 2, let's combine the real parts, plus j omega, minus angle sigma plus j omega, and minus angle sigma plus 1 plus j omega, and that's gonna be 2n plus 1 times pi. No issues there whatsoever, right? All right, so now what is the angle here? Of course, that's gonna be tan inverse omega by sigma plus 2 minus, this is going to be tan inverse, again imaginary part by real part. Again we are skipping that portion where we would have to write plus minus pi to make sure that the angle falls into the principal value, but again we are imagining that is being taken care of by this. Again minute mathematical details here. Tan inverse, we have tan inverse omega by sigma plus 1, and that is going to be 2n plus 1 times pi. So once we have taken care of that, now we have to ensure that we understand something very important here, that how many principal valued angles do I have here. So how many principal valued angles do I have? I have one tan here, one here, one here, right? So we are kind of going to assume at this point is that again the principal value, just to make sure that you understand, tan inverse x falls between minus pi by 2 and plus pi by 2. So that's called the principal value of inverse circular functions. So just open your class 11's books, you will see that these are there already. So that's the principal value called. Okay, so this is going to be between minus pi by 2 plus pi by 2, this is going to be between minus pi by 2 plus pi by 2, this is going to be between minus pi by 2 plus pi by 2. So that way this cannot this sum cannot really be beyond something like plus pi minus pi, right? This is going to be between plus pi minus pi, something like that. So for our purpose, let's just write pi here. Okay, so we are settling with the value of n equal to 0. If that doesn't work, we're going to add 2 pi or minus 2 pi with our calculation, because essentially as long as the geometry or trigonometry is concerned, pi is equivalent to 3 pi, 5 pi, minus 3 pi, same thing, right? Minus pi whatsoever, right? So these are equivalent really. All right, so now we have to do a little bit of what should I say, calculation. Let's write tan inverse omega, clever calculations now. Tan inverse omega by sigma plus 1, and that's pi plus tan inverse omega by sigma. All right, that's tan inverse. All right, so now let's use the formula for sum of two tan inverse. So tan inverse x minus tan inverse y, you know that already, and that's tan inverse x minus y divided by 1 plus xy, and this is pi plus tan inverse omega by sigma. I'm leaving it as it is for the moment, but you have to understand that we're going to use this idea. But I could have simplified this further very easily at this very point, but I'm not going to do that. All right, so we have tan inverse, something big here. So if I simplify this here, so on the denominator I get sigma plus 2 times sigma plus 1, so that's going to be fixed for both of them, and omega I would have sigma plus 1 minus sigma minus 2, sigma plus 1 minus sigma minus 2, and here this is going to be sigma plus 2 times sigma sigma plus sigma plus 1 plus omega square. All right, I think that's fine, and this is going to be pi plus tan inverse omega by sigma. Okay, now there is one interesting thing I'm going to do here. I'm going to bring this tan inverse to the right hand side. I'm going to bring this tan inverse to the right hand side. Again, please follow the calculations carefully. I have a possibility of messing things up. All right, so I have this, I am bringing this to the right hand side. So this is again an equation. Now if I bring this to the right hand side, it becomes tan, right? So essentially I'm taking tan over the whole thing, right? So it is becoming tan pi plus, now this is just an angle, right? Tan inverse omega by sigma, that's an angle. Let's just say theta, right? Let's just say theta. And if I say tan pi plus theta, what is tan pi plus theta? What is tan pi plus theta? Right? Yes, if you have guessed it is to be tan theta, you are right, right? So tan pi plus theta is essentially tan theta, right? You know that, right? So that's going to be tan theta. So this is going to be just tan theta. But what is tan theta? Because I said that this is theta, right? I said tan inverse omega by sigma is equal to theta. Then what is tan theta? Tan theta is just omega by sigma. Omega by sigma is tan theta. So essentially this is tan theta, which is omega by sigma. So if I just bring this side, this to the right hand side, this just becomes omega by sigma. Is there any confusion with this? I don't think so, right? So here I am just simply writing omega by sigma, right? Pretty simple calculation, right? Easy to understand. But now here omega cannot be equal to 0, right? We are on the j omega, on the complex plane, but we are not on the real line, right? So since omega cannot be 0, I can cancel out omega from both sides. So this can be cancelled out since omega is not equal to 0, right? That cancelling can happen since omega is not equal to 0. We are ensuring that omega is not equal to 0 by not staying on the real line. If we are on the real line, omega is 0, right? But omega is not 0 in particular case because we are already between the breakaway and break-in points, right? So let's do the simplification once more. So with that, we have sigma minus sigma. So that's minus 1, I think. That's minus 1. And here we have sigma square. Right? We have sigma square plus, how much is it? Plus 3 sigma plus 2 sigma plus 2 plus omega square, all right, and that's equal to 1 by sigma. I don't think I have made any mistake. I could, not entirely sure. Sure though, let's see. All right, so right, nice calculation, right? So sigma square. Please make sure to tell me if I have made any mistake in calculating things. Let's do the cross multiplication. So sigma square plus 3 sigma plus 2 plus omega square is equal to minus sigma, and let's bring out another page here. All right, so let's bring this to the left hand side here. So minus sigma is brought to the left hand side, becomes 4 sigma, and we have plus 2 plus omega square equal to 0, and this is sigma square plus 4 sigma. And in order to make this a whole square, a perfect square, I would write 4 here, right? Of course you understand what I'm saying here, right? And plus omega square. So I wrote 4 here instead of 2, so I have to add 2 on the right hand side as well. So this equation is now correct. So now again, so this is sigma plus 2 whole square plus omega square, and that's equal to root 2 whole square. But what kind of conic section does this equation represent, right? What kind of conic section does this equation represent? And if you said this is a circle, you are right. This is a circle indeed. Circle with center at minus 2 comma 0. Of course its center is at minus 2 comma 0, and radius equal to root 2 unit. Got it? So it's a circle centered at minus 2 comma 0 of course on the S plane, and it has a root 2 unit of radius. But what is root 2? Root 2, so radius is root 2. Essentially radius is 1.414 units, right? It's a circle, and radius is 1.414 unit, centered at -2, 0, right? But what are we just trying to figure out? We are trying to figure out the locus of the roots when the breakaway happens, but after the breakaway happens, and before the break-in happens. So we just figured out that after the breakaway happens and before the break-in happens, it is a circle centered at -2, and the radius is root 2. And it just so happens that this length, okay, this length, look at this very length from this center. So this is the center of the circle. And from this center, what is this length? Look at this point. What is this point? -3.414. So what is this length? This length is 1.414. And what about this length from the break-in point? This point is at -0.586. But from -2, how far away is this point? 1.414. So if I draw the circle that I just designated, okay, around this center with this radius of 1.414 unit, so this will pass through the breakaway and break-in points, and this is exactly what is going to happen. Let me draw the circle. Nice. And this is my technique of drawing a circle. Okay, you have seen my technique of drawing circles, right? Oh, right, that kind of looks okay, I think. Nice. So can you tell me what just happened? So this was the breakaway point and this is the break-in point. So after the breakaway, see, look at the very point here, look at the very vicinity here. After the breakaway is happening at 90 degrees, because look at this very point here. If you zoom in, okay, you will see that this is 90-degree breakaway, so it is not violated, and this is a 90-degree break-in, no problem. Then they are essentially breaking away at 90 degrees, going in this direction, approaching in this direction, and then they are breaking in. Now these two routes are breaking in at this point, then they have to go somewhere. So one of the routes would approach the open loop 0 in this direction, and another route is going to approach the asymptote. So this is the root locus. This is the total root locus here. Okay, this is the entire root locus. So try to understand what just happened here. Okay, so these are the starting points. So when k was equal to 0, so let's now mark everything on this. Okay, so this is at k equal to 0. Okay, very thick. This is at k equal to 0, and this is at k equal to 0. So when k is equal to 0, the roots of the closed loop system started at -1 and 0, which are essentially the open loop poles. But as the gain increased, they approached each other. Okay, they approached each other, and at gain k equal to 0.172, they met at the point s equal to -0.586, and that was the breakaway point from which they broke away, and then they become complex conjugate pole pairs following a circle. Okay, they followed a circle, and then when the gain became 5.828, they met again on the real axis at the point s equal to -3.414, and from there, as the gain went on to become infinity, one of the roots approached s equal to -2, which is one of the open loop zeros, and the other one followed the asymptote. That is the root locus of this system. Right? Tell me if you understood this, or tell me if you have any query with this. I have also applied k tending to infinity here. So this is the loci of the roots. We have two roots, and this is how they travel. So let me write down the story of this. Okay. So let me write down the story. So if I write down the story of this particular system, so we are saying that when k is between 0 and 0.172, it is overdamped. Yes, there is someone is asking, is it possible to say which root goes to which? There is absolutely no way of saying which root goes to which, because when they break in or break away, they are identical roots. They become identical. Okay, so one root becomes indistinguishable from the other. So there is no way of saying that this root might have gone up and this root might have gone down, or this root might have gone up and this root might have gone down. There is absolutely no way of saying that, saying those. So in that way, there is really no way of really saying that. Okay, because the roots become indistinguishable from each other, right? So you cannot really say anything like that. So when the between these two between 0 and 1.78 1.0.172, the roots are real and unequal here. Okay, so overdamped, and at k equal to 0.172 we have two equal and real roots, so critically damped. And when it is beyond that but less than 5.828, these are complex conjugate pole pairs, so underdamped. And at k equal to 5.828, they are once again critically damped, but the undamped natural frequency is different, right? The undamped natural frequency here and here are different, so you have to draw circles through the origin to figure out the undamped natural frequency. And also you know the undamped natural frequency, right? Here at this critically damped point, the undamped natural frequency is 0.586 radian per second, and here the undamped natural frequency is 3.14 radian per second, right? So again critically damped. And along this, after that, so k greater than 5.828, once again one of the poles are here, one of the poles would be here and the other would be here, so real and unequal poles, so overdamped. So that is what we have figured out about the system. See, none of this could have been figured out using Routh-Hurwitz alone, right? In fact, Routh-Hurwitz only played a role of saying that the system cannot be unstable at any given value of k as long as k is positive. That is the role. That is the entire role Routh-Hurwitz played in this one, right? And if you draw the S grid on top of it, you will be able to figure out the exact values of damping ratio and everything at any points. So as I was saying, rule number 5 really talks about, so rule number 5 is done. So let's talk about rule number 6. So rule number 6 essentially we have just figured out. So this is rule number 6. Did I write anywhere? So rule number 6. So rule number 6 is for the existence of circles on the root locus. Root locus. And this is how you figure out existence of circles on the root locus. This is again more of a construction rule rather than a rule that must be there, right? So there are certain rules that must be followed. For example, rule number 1 must always be followed. For example, it says the root locus is symmetric about the real axis. That must always be true. Okay. Rule number 2 says that the root locus should start from here and end there. This part is on the real axis and everything, right? So with that said, this is again an optional rule. It might satisfy, might be there for a particular root locus, might not be there for a particular root locus, but yeah. All right. So there are 4 more rules that we're going to see. Rather, I would say 3 more rules because we combined 2 here before, right? Anyway, so we're going to more or less end our rules section. Okay, someone is asking a very important question. Does it mean that for this one? Does it mean that when k goes to infinity, one of the roots is at -2? Yes, absolutely. We figured that out. When k goes to infinity, one of the roots is going to be -2. And the other is going to approach the asymptote and go to infinity. So when k approaches infinity, one of the roots is finite in this case, and this is -2. And the other root is going to be approaching -infinity. Okay? And this way. So that's true. Because that is one of the things I said here. If you go back to the very discussion here, he said, okay, what about the rules of the asymptotes? I think I wrote it on the rules of the asymptotes. Yeah, we said as k approaches infinity, the roots approach infinity along the asymptotes. If there are finite open loop zeros, then there would be poles that approach the open loop zeros as k tending to infinity, and the rest would approach the asymptotes, right? So if you have a system that has, say for example, 5 open loop poles and 2 open loop zeros, okay, 5 open loop poles and 2 open loop zeros, then the root locus would start from the open loop poles, locations of the open loop poles. But as k approaches infinity, 2 of the poles would end up reaching the open loop zeros, locations of the open loop zeros, and the rest 3 would follow along the 3 asymptotes of the system. Okay, that is how the asymptotes work. Asymptotes are for those poles which do not find any zeros, for example, right? So if you have 3 number of zeros, 2 number of zeros and 5 number of poles, then 2 of the poles would approach the zeros as k approaches infinity, and the rest 3 would approach the asymptotes and follow along the asymptotes and go to infinity from different directions. And yes, since this example, in this particular example, I have a finite open loop zero. So one of the poles approached that, okay, as k tends to infinity, and the other went to infinity from the negative side, approach the asymptote, right? So that's the end of today's discussion, and we are going to continue with this on the next week. So again, feel free to ask any question that you might have, and let me know if we can arrange any additional discussion on Google Meet or anything on this week, maybe this Saturday. All right, so thank you very much. It's already been 2.5 hours, and we're going to end the discussion right now. If you have any query, just drop me an email. I will be definitely answering your queries. And again, this handouts will be available in the video description. Thank you very much. I'll see you next week.